All right, good. So I didn't know what I should really present, so I thought I'd just tell you a bit about everything we are currently doing in our Meteor research group of the European Space Agency. I list a number of names. You see a number of familiar names like Teresa and Esther is on there because this is basically all the people that have ever been working with us, and our Meteor group simply grows and grows. And the latest addition we have to the group is Sarah Jouaret. She is starting or will be starting 1st of October. And maybe Sarah, you could show your video quickly so that people see you, because I think it's also your first IMC. Yeah, there she is. So, okay, good. All right, so let me go through the presentation and show you a bit what we are doing. Some of the stuff should look familiar because we presented it earlier. Our main asset is called CILBO, Canary Island Long-Baseline Observatory. That's a double station meteor camera set up on Tenerife. It's been operational for about 8 years. It's right now not going so well anymore. So we see degradation. It uses image intensifiers where we had already one replaced and the other ones are degrading. I guess everything is dirty, but okay, still we do some good work, and we had a number of publications in scientific journals. We are focusing, or we're focusing on flux densities of meteoroids. Okay, I work in a space agency, so it makes sense to be interested in that because there's always this question, could something become dangerous to satellites? And you know, the green dashed line here is the so-called green curve, which is green in German, but it's actually the name of a person who modeled this flux density a long time ago. Depending on which luminous efficiency we use, we can find out whether these numbers make sense using our techniques. Okay, I do this, so to say, half professionally, half as an amateur. This is definitely, of course, one of the more professional projects. We're looking at lunar impact flashes. We're looking at the dark side of the moon, and I do mean the dark side. That's namely the unilluminated side, has nothing to do with the far side. We always run into trouble when we tell that to the public. Oh, how can you see the dark side? It's on the back of the moon. Of course not. This project NELIOTA, if you Google for it, you should immediately find a hit. Uses a 1.2 meter telescope in Greece. And via a dichroic beam splitter, we have two cameras that record the dark side of the moon. And you see me here in the operator room. This is actually the dark side of the moon. Because of earth shine, you still see something. And then what's really white here, that's stray light coming from the illuminated part of the moon. And these guys have developed a mechanism to detect impact flashes, and Pete Gural was helping us there in the beginning. So thank you, Pete. In the meantime, the system has been operating for about 3 years, and it's amazing how little observing time you get if you want to see the dark side of the moon. We have something like 120 hours, and in that time, we have also about 120 impact flashes. So on average, for 1 hour observing time, we see one flash. There is an example, it's at the edge of the field, but I still pick this example because it's one of the events where we have really a number of frames where we record the event. And then with the two different color channels, if you assume that you have a black body radiation, you can determine the temperature of the impact flashes. And that was the paper that I cited before on the previous graph, where we come up with the first, I forgot, 60 impacts, we determined the temperatures. Another thing I'm still trying to push while I'm in the European Space Agency is that we actually get a camera into space that looks back to the Earth and observes fireballs. We were doing a number of breadboard work. This one down here is a camera that was built by Jena Optronic with I think 90-degree field of view lens working in the near infrared. And we had a master's thesis together with the University of Oldenburg. And here you see a meteor observed with one of our intensified video cameras just in the normal visible. And here is the same meteor in the infrared or in the near infrared. So this master student spent, I think, 3 nights out during the proceeds and could record 20 meteors in the infrared. This camera is very noisy, as you can see. All these white dots is simply noise, so it's not easy. And I now have funding actually from the Planetary Defense Office of ESA that we can build a flight model for such a fireball camera. We then need to find a flight opportunity for that, but at least there's money there for building something. I doubt that it will be in the infrared. I think it will just be in the visible. Infrasound, we heard a couple of presentations. We managed over the last years to set up quite a regular, well, let me call it service to use infrasound data, where again, University of Oldenburg is involved, and Esther and Teresa were giving a presentation already, not on this topic, but they were also involved or are still involved. We have access to the infrasound data, and whenever there is a bright fireball, Esther and Teresa are checking whether we see a signature in the infrasound. And down here you see a screenshot where this ends up. Basically, the information is then posted on the IMO webpage. So we really think it's very good that we have the IMO as the key information distribution point here. It's just a screenshot from one of these events, which was a bright fireball in this area here, where this thing was also observed by some lightning sensors from satellites, and then the infrasound reconstruction really pinned down the location very well. Spectra, well, you heard Regina talking about fireballs. Before she started with this NEMO system, she was looking at spectra. With our station on the Canary Islands, we have one camera with an objective grading. And in the beginning, what Regina did was, this is a spectrum as we see it, and we had a user interface where you can type in numbers and abundances, and then you basically say, okay, let's assume a background with a certain temperature, and then let's add some elements. And then in the end, when you're happy, you know what the chemical composition, or at least what some of the elemental abundances are of these meteoroids that we see. We had a master student at the University of Delft, supervised by my colleague Joe Zender, and he did a bit more professional way. Well, I think that was professional enough, just doing it manually, but maybe not the most efficient way. Now we have a tool which helps us doing this more automated than we were doing it before. And this is a typical spectrum, and then you just let some computer software running. It's based on Bayesian inference, and then you get the result. This is my favorite topic, which I really want to continue, looking at the error bars for orbital elements. We heard this discussion on interstellar meteors. I mean, for that, it's super important to know the error bars. And here you see some Geminid data. I looked at all the Geminid observations that we had. And we did a Monte Carlo simulation, just assuming a certain measurement uncertainty. Yeah, thank you. And then I can compute the orbital elements based on different measurement uncertainties. And you get these plots here, which show you also you are not allowed to take the mean value. You always have to take the median, because if I take the mean of all this, then my average point ends up here, which is physically impossible. So always use the mean when you do something like this. And here you see a bit the error bars that we have in our velocities. Adlene, who just gave a presentation before, she also did her master's thesis at the University of Oldenburg, and it was about debiasing the Meteor radiant distribution. If you look at some of the data, you know that we have this apex source and a toroidal source and whatnot for the sporadic meteors. We are trying to sort of take into account all the observational biases and then come up with a radiant distribution. Now it's a bit more homogeneous, but you still see an effect. So we are not yet really done there. So there's plenty of additional work. You heard the work on luminous efficiencies based on Friedpont data. You heard what we do on fireballs. We have 2 all-sky cameras, unfortunately those which had a bad batch of video cameras which don't work fine, so they're still not operational. We're also expanding Fribourg in the Netherlands. We need to install one camera at Felix's place next. So that's all things we are working on. And I already welcomed our new young graduate trainee. And when I thought a bit about what we can do, I mean, Sarah, you will not be bored because we have about 15 points. And if I spend 5 more minutes thinking about this, we'll have much more that is still possible to do. Having said that, at ESA, we always have these possibilities for internships, and now would be the time to apply for them, because I think there's a deadline in October or November then for next year. So if anybody is interested, just drop me a mail. Thank you very much for your attention.
Thank you.
No,
perfect timing. This has been space science. With perfect timing. I would jump straight onto you with the question about this Meteor fireball camera from space. Can you imagine that as something like a CubeSat based cheap solution? I mean, like, you know, 3 unit or 6 unit or 12 unit something? Or would that be a separate, what is not the payload, but the other side, the platform? What is the planned platform?
It could be possible. I mean, the thing that worries me with CubeSats is the stability, the pointing stability. That's something where I'm not sure how good that is, but I know there are studies going on. If you ask Jeremy, I'm sure he will tell you a lot about it. There's a group in Stuttgart that's doing that. There was a proposal to the European Union a few years ago, using 2 CubeSats flying in formation. It's possible. I mean, the breadboards that we have would fit into, say, I think with a 12-unit CubeSat, maybe even a 6-unit, you could do the whole thing. I mean, with attitude control and what have you. It should be possible. I mean, we were thinking more in terms of a hosted payload. So say on a larger satellite, say a weather satellite or something, because we may want to end up in geostationary orbit. Most CubeSats are simply deployed in low Earth orbits. So, but it's a possibility. I don't want to exclude it.
All right, thank you.